Is started, and then what we'll do today is what I'm doing yesterday. So the Monday Wednesday class has finally caught up with you guys, so we are in sync now at this point. Okay, so what we'll do today is we are going to take a look at the execution of a particular instruction today in this class. And that instruction is going to be the LDI instruction. All right, so let's go ahead and get started here. For the most part, I don't need to access Canvas anymore during class because I'm not writing modules, because these are really difficult to describe in words. And if I do describe these things in words, it will be harder to understand as well. It's much better for me to show it in Logisim, and then you guys can take notes, as you see fit. Okay, so I do recommend that you guys take notes, but I don't know exactly how or what notes you should take in addition to the recording of my voice as well as the screen during class.
It is recording, right?
It is recording. It's recording the fact that I am saying that it is recording, yes. But that's not recursion. Okay. So we'll go ahead and go to the Google Drive, because most things are now on the Google Drive as well as in Logisim. So those two become the most important resource. The class recording obviously is another really important resource at this point. When I say something is important, or when I say something repeated several times, it typically means it is significant. Okay, so you might want to jot that down. When I talk about a particular concept, you might want to jot down the time, when that happens, so that on your notes, you have a time index, so that when you go back and watch the videos again, oh, okay, I just need to refresh on that part. You know where to go to within the 80 minutes of the entire recording of the class. So that's how I would utilize the resources. How I would utilize your own notes. All right, so let's go ahead and go to the cisp310 folder. Okay. So cisp310, and within the shared folder is the processor subfolder. And within the processor subfolder, we basically have everything that we need for this class at this point. So let me close off the other tabs first, because otherwise they're just going to be distracting, because we will need multiple tabs in this class. So I'm going to close off most of these tabs. So in the lab activity, you are going to learn how to utilize the tool chain. I call this a tool chain, which includes the documentation, the simulator itself, the processor that is running inside Logisim, and also the assembler. Okay, so the assembler is also a key component. You probably want to either bookmark or have your own copy of some of these documents. Opcode table is one, so I'm going to open up opcode table by itself. Another one is going to be the assembler manual. Okay, so these two are basically documentation resources. And then the third one, which is the one that you're going to have to use for the rest of this semester, is the assembler itself. Now, for the assembler, we're not going to do anything for now because I want to go to the opcode table first. And today we're going to talk about the LDI instruction. So you can see, oh, this is great. I'm glad that you guys are using this resource, because that's what it's for. I think more classes should really start to use Google Documents as a way to teach classes, because it allows you guys to go to the same document. So when I'm looking at a particular portion, you can be looking at a different portion. You can go back and forth, all you want and stuff like that. You can make your own copy. You can make a copy into your own folder. Then you can annotate. You can add your own notes. Do whatever you want with it. So what we want to do is to talk about the LDI instruction today. So I'm going to locate the LDI instruction. Did I skip 24? Okay. All right. Thank you. So the LDI instruction is this one. Let me magnify so that we can just kind of focus on this one. There we go. So when we look at this particular spreadsheet, this spreadsheet is not for automation. It is not the assembler, it is intended for people to read. Column A is the bit pattern of instructions. Column B is what we call the mnemonics. Okay, it's basically a symbolic shorthand so that you don't have to remember, oh, LDI is 01111, and then the 2 bits to specify which register we're going to change. So instead of remembering the bit pattern, you can say, oh, LD is load, I is immediate, so load immediate. X is a register, it can be from A to D, because we have 4 registers in the register bank. And then I is an immediate, which means it is a constant. Okay, it's just a number, it is a constant. It can be a label too, but later on we'll talk about how we can use a label. But for now, we'll just say that I is just a number. Okay, like 30, 26. Okay? All right. Column C can be confusing because column C is really saying what the instruction is doing. So in this case, it says x equals to, and then the dereference, and then inside the dereference is PC++. So it's a post increment of PC as a register. PC stands for program counter, by the way. Or the other way to look at this is the other one. I just added this yesterday. So if you made a copy of this document before yesterday, you might want to make another copy because I changed it a little bit. Okay, there we go. All right. So the other document, or the other way to represent this is to say x equals to RAM. In other words, we are getting some content in RAM. Which content, which location are we getting in RAM? That is, this is using the C and C++ syntax. The square bracket is indexing. So PC as a register is supplying the value that we are going to use as the index. And then the post increment means the program counter is incremented after we get the content of RAM. Well, at least after we use PC or the program counter as an index. So is that okay? And then this comment here is basically saying, whatever the PC is pointing to at the beginning of this entire sequence is where the immediate constant is located. Yep.
How large can the constant be?
It is only within a byte, so it can go from 0 to 255. And the way I code it, I think it can only deal with unsigned base 10 numbers. Now, if I have time, I might throw in hexadecimal and binary and some other bases too. But at this point, it can only handle base 10 numbers. Yep.
The reason for the postfix increment, that's just because the program counter is going to advance before it runs, right?
Right, because the program counter is always pointing to the next instruction. So if this byte is not a instruction or it is a part of one instruction and we have used it already, then it has to advance to the next location so that in the next cycle we are ready to read and decode the next instruction. So that's a very good point. That's exactly why we have a plus plus. Okay, so are we doing okay so far with the overall description of the LDI instruction? Sort of, okay. So I'm going to take you guys through the whole tool chain. So let's say I'm going to use a notepad here. So let's say I want to implement or I want to test an instruction, which is LDI D, 16. Let's make it 161. Okay. So let me write it here so that we can talk about it and you can see it. There we go. Okay, so the instruction that I want to use is LDI, register D, and 161, which effectively is saying, okay, I want to initialize register D so that it has a value of 161 in base 10. Now, all the numbers are in base 10, when you write the code. So the first question is, well, this is easy to read, but how do we know what bytes we need to put into RAM in order to represent this particular instruction? So that's a question that we have to answer. What do you think? So LDI, has an opcode of 01011XX, and these 2 bits, the XX, is here to designate which register we want to use in this particular instruction. So if register A is 00, what do you think is going to represent register D in base 2? 11. Very good. Okay, so we have an idea now. So the opcode itself is 0111111. Okay, so these 2 ones are here to designate which register is affected by this opcode. If we want, register A, those 2 bits will be 0, 0. Okay? But they also need a second byte. The second byte is the actual immediate value that we want to copy to register D in this case, and it is 161 in base 10. So how do you translate 161 in base 10 to hexadecimal or binary? Let's do in that hexadecimal first, okay, because that is actually easier. It's easy because 161, if I want to express it as a multiple of powers of 16, how would you do that? Okay, how many 16s do we have in 160? 10 of them. Okay, but in hexadecimal, it is using which digit to represent the value of 10? A. Okay, so 0xa is the first digit. And then we are left with just 1. How do we represent 1 as a hexadecimal number? 1. Very good. Okay. That was a trick question, by the way.
Should it be like capital A or?
It doesn't matter because we are not using, because we want to translate this into binary representation. So in binary, A is 1010 because it's A plus 2, and then the 1 is 0001. So these 2 bytes in binary is representing this particular instruction. So my question to you is, would you rather be able to program or write programs like this, or would you rather have to translate everything yourselves into bit patterns like that? The top one. Okay, I like that. Okay, so you would prefer everything to be more symbolic and have a mechanical translator to basically perform all the translations for you. That's good. That makes sense to me. And before we move on, I'm going to show you one thing. How come I have so many tabs here? Okay, they're just browsing. Okay, they're file browsers and command line interfaces and stuff like that. So before we move on, I want to show you the Altair computer. Altair, I think, 8800. And this is a good picture. I always use this picture. It doesn't have that button anymore to only show the picture, so I can use this instead. There we go. Okay, so if you look at this particular computer, if I tell you this is the user interface right here, okay, it's not like this computer has a hidden Bluetooth capability, so you can say, oh, we can use a Bluetooth mouse and a Bluetooth keyboard to program it, and then the monitor is wireless. It is using Wi-Fi to remotely connect to the computer. No, there's no such thing. Okay, everything is wired. Okay, so this is your entire user interface. How do you think you're going to program this thing? How do you insert instructions into memory in this case? There's a lot of switches, don't you think? So one switch is 1 bit. You specify the location using the switches. You specify the content at that location using the switches. And then there's one switch that says, okay, clock in. Rising edge, right? Stores. So that is how you program the Altair 8800 computer. So imagine that you have to enter a program that is like 16 kilobytes. So that's 16,000 locations, and then each location has at least, well, not 16, but at least 15 bits for the address, and then 8 bits for the actual content. And if you mess up, it doesn't show you anything, right? That instruction is just entered incorrectly. Yep. So count yourself lucky that we have an assembler, so that you don't have to do something like this. Okay? So I just like this picture every single time I get to this point of this class, because if someone's going to complain, go like, do we really have to program like this? Yep. Okay, so this is a good time to go into the assembler. So in the assembler, there are multiple tabs or multiple sheets within the document. You go to the one that is source, okay, that says source, And here we can, this is from the previous class, so we're going to erase this. And then if you type something wrong, okay, so if you just have a number like 80 here, it's going to complain and say, oh, okay, I don't recognize that. So you do have to make sure you enter the LDI instruction. But if you just enter the instruction, but without providing what we call the operand, it will complain about it. And it tells you that the register itself is missing, and the immediate constant is also missing. Okay? It took me quite a bit of work to make it report problems like these. But it does a fairly good job with this stuff. So we're going to put in a D and then 161 here, and then the error message would go away because this is the correct syntax. So the program is okay now. Okay, the opcode, the mnemonics are fine. You can also use / if you want to insert comments. Okay, LDI D161. Okay, and I can just use comments which starts with // which is the same standard as in C++, and then you can type whatever you want. Okay, D is 161. Okay, that's cool too. In other words, everything that is after // including the / itself, is ignored. It's just comments. You can comment your program so that you don't lose track of what your program is doing. Do we have any questions at this point about how to use the assembler? You can also type your program in a text editor and then just Control A, select all, Control C, copy, get in here, go to cell A1, Control V to paste. That works too. So that means when you are writing your program, that you don't have to write it inside the spreadsheet. You can write it outside of the spreadsheet and then just paste it in. All right, so I'm just going to skip to the RAM file tab here, and it looks like this. This is the actual content of a text file that Logisim can import into the RAM component. So if it doesn't complain, if it complains, this cell here is not going to say v2.0 raw. It will complain and say there are errors. Okay, you can tell that it will complain about there are errors by the cell equation itself, or the cell formula. See how the cell formula is having an if statement, and it complains that there are errors. That's the message that you will see when there are actually errors. But when there are no errors, the else part of that conditional statement is v2.0 raw, and that's what we are seeing right now, which means we don't have any errors. This spreadsheet, for those of you who like to learn how to use spreadsheets, this spreadsheet does make use of a lot of kind of odd and rarely used functions in the regular spreadsheet. So if you read into the spreadsheet itself, you can learn how to use a spreadsheet for complex tasks like like an assembler. It's open sourced. The whole thing is completely open. All right, so at this point we can do a file. You go to download as, and then just choose one of the last two options, comma separated value or tab separated value. Either one is fine because we don't really have multiple cells on the same row. So I chose the first one, and it is now saved. It's by default saved to the downloads folder. Then I can switch back to Logisim, and I don't think I have it started yet. So we'll go ahead and start it. So jar downloads. Nope, it's not in the downloads folder. This is actually in the. There we go. So inside Logisim, you have to go to the folder that contains the processor wdpc2.circ file. Okay, so wherever you download it to, you just have to go to that folder. I put it into my processor subfolder, but you can put it anywhere you want. Okay, so now we have the processor. Before you load the content into RAM, it is always a good idea to reset the entire simulator first. Control R would do that. So I just did that. Now Control R would also clear the content of RAM, and that's why you only do it if you're ready to reload the content of RAM. So right click, go to load image, and then we locate the file that we just downloaded earlier, which is in my downloads folder called assembler ramfile.csv. Click open, And now we have those 3 bytes in RAM. So now the program is ready to execute. So this is the easy part. The actual part that is kind of difficult and will take time is to explain, okay, now that we have the program loaded into RAM, when we execute this program, what is going on in the processor. And I'm going to show that and explain it to you, not clock by clock, okay, but edge by edge. In other words, I'll explain what is happening with a rising edge, what is going on with a falling edge, what's happening with the rising edge again, and so on. There's a lot of details, okay? So the best thing you can probably do is to kind of follow along in the discussion and ask questions when you say, okay, I don't quite understand what that was, okay? Could you explain that again? So that would be a good use of your resources at this point. To start with, we always start with this portion of the processor, okay? This is what we call the quote-unquote microcode engine, or the microcode control mechanism, or the controller of the processor. In other words, this is the conductor when the rest of the processor is the orchestra. This is the part that coordinates everything else. Okay? If you look at this, this is kind of the score that the conductor is playing out of, and this mechanism here is kind of like the metronome, okay? It keeps the beat so that the conductor knows, okay, this is 1 beat, this is 1 beat, this is 1 beat, okay? When you look at this component, these components here, the microcode pointer, and this is an adder, this forms a very basic counter, okay? So if you don't take the multiplexer into consideration and just pretend the multiplexer is always connecting input 1 to its output, then this becomes really just a regular counter. So for every clock falling edge, it's going to increment, not rising edge. The reason why it is only going to do it in a falling edge is because that is how it is specified. The trigger of the microcode pointer is going to trigger on a falling edge. This is the only register that does that in a falling edge. All the other registers are sensitive to rising edge instead. So are we doing okay so far with this part? Are there any questions about the counter part of the microcode pointer? No questions? All right. What is the output of the microcode pointer? What is its job?
To select the microcode to be used for the proper opcode instruction.
Exactly, because it connects to the A port or the address port of the ROM. So you can see how the output of this particular register, the Q port, connects to the A port of the ROM. And the A port of the ROM is basically the index of that particular thing. It allows you to say, okay, which location should we look at? That is what the A port is doing. Okay, which page should we turn to? And you can see that the microcode pointer currently has the value of 0, 0, 0, and as a result, the location 0, 0, 0 is now addressed. I kind of paused a little bit, I hesitated a little bit because I was about to say the byte, but it's not a byte. This is kind of a really odd number because when you click on the ROM component, you can see that the data width of the ROM is 26 bits. So it's kind of odd, okay? It's not 8, 16, or 32. It's just 26 because 26 is what I need for this processor to work. So right now it is addressing location 0, 0, 0, and the content at that location is in hexadecimal 1080007, and that is now presented to the data port. So how do we know it is presented to the data port? Well, the quick and easy way to do it is to go use the poke tool, and then you click on this wire, and you will see that it is now represented in binary, but it's basically the same thing. This is the 1, 0, 8, 0, 0, 0, 7. And then you guys are going like, yeah, but we can see it next to it too. But that's only because I changed the default to print in hexadecimal. If you do not do that with your own logisim, it's going to display this as a signed base 10 representation, which is not going to be clean like that. It's going to be one messy number. Is that okay so far? Okay? All right, so the conductor has made a gesture, okay? What is that gesture going to do to the rest of the processor? So now here's the tedious part, okay? It is not like it is really, really hard. It is just tedious. Because we have talked about every single component in the processor already, and now it is the time to just to figure out, okay, how do they work together? That becomes the kind of the key issue. So now you have to look at all the key components and say, okay, who's active? Who's going to do something at this point? Well, the enable and the select, those are the ones that you have to watch for first. Okay, depending on the component, sometimes it's called EN for enable, other times it's SEL for select. For the register bank, which is this particular component, you can see that none of the EN is enabled. This EN, input enable, is off. It is dark green. It is a 0. Register output 0 enable is also off. Okay, it's a dark green. So the register bank, for the most part, is inactive. It's not doing anything. This is our ALU, or the arithmetic and logic unit. Do you think it is enabled?
No.
Why? How do we know it's not enabled?
Wires dark green.
The wire going to EN for enable is dark green. Okay, cool. So it's pretty easy to tell whether something is enabled or not just from the color of the wire going into the EN port. Let's take a look at some registers. Okay, this is the flags register. Do you think it is enabled? No, because EN, which is this wire, is a 0. We can look at the program counter, which is all the way down here. It is also not enabled because EN is a 0. We can look at the instruction register right here. It is enabled because the EN going into the instruction register is bright green, which means it's a 1, which means on the next rising edge, it's going to update itself. So we'll try to figure out how it's going to update itself now. So that's how you look at things, is you keep looking for something that is going to be active, that's going to do something, and then you ask, okay, I know it's going to do something. What is it going to do? Okay, with a register, there's not much it can do, right? It always outputs its own content. That's not something that you can enable or disable. So the only thing that you can enable is to change it. So now the question is, we know we're going to change it in the next rising edge. How are we changing it? In other words, where are we getting the value to change the instruction register? That becomes the next question. Is that making any sense? The way I analyze the circuit? Okay. So you look at the D port, you click on the wire of the D port. This is one feature of Logisim that I really like a lot, is when you click on a particular wire, it will highlight everything that is connected to that particular wire, including everything that connects to the same tunnel. So this is highlighting everything that potentially is currently connected to the D port of the instruction register. Okay, so you look at all of these things and go like, okay, who can possibly be driving the wire? Who can be presenting content at this point? So let's go from the left to right. Okay, this is a multiplexer. With a multiplexer, is it multiple input or multiple output? Multiple input. Can an input be driving a wire? Nope. Okay, so we know the multiplexer is not going to do anything. The next one right here is also a multiplexer. It also connects to one of the inputs. That's not going to drive the wire. Over here, we do have one demultiplexer that can potentially be driving the wire. But when you look at the enable of the demultiplexer, it is disabled. So that means the demultiplexer, even though potentially it can drive this wire, right now it is not driving this wire. Okay, so we have looked at everything in this part of the picture and nothing is driving the wire. But when you click on the wire, it clearly has some content on it. So something is driving it. Yep.
What do you mean by driving the wire?
Specifying content on the wire. So now we slide to the right hand side. And now we find the other component that can also be driving the wire. Now this one is kind of difficult to deal with. Because it's the data port of RAM. It can be input or output, okay? So when you're dealing with RAM, the first question is it active? Is this component active? This is the one component that has SEL instead of EN, but it serves the same purpose. So the RAM component is in fact active because its select port is a 1. Okay, so now that you know the RAM component is active, the next question is, are we reading from RAM or are we writing to RAM? Because that direction changes whether the D port is driving or whether it is sensing. What do you think?
Load is on, so it's
The LD is a 1, which means we are
reading out from it.
we're reading. We're reading from RAM, which means the RAM is driving the D port.
Yeah.
Okay? So if RAM is driving the D port, what content is it putting onto the D port? Whatever is getting addressed, right? Okay, so we can see it's highlighting location 00, and so 6F is on this wire. Now we can double check that, right? We can click on the wire and go like, okay, are we seeing 6F? Remember, yours, unless you change your configuration, you're not going to see the 6F here. So we have to look at the binary number and make sure that it is 6F. 0110 is 6, 1111 is F. So indeed, we do have 6F here. But then there's another question now. Because why are we addressing location 00? Who is specifying, who is telling RAM and say, hey, turn to page 00, that's what we want. So, well, no, you have to track down the A port, right? Because the A port of RAM is the one that specifies which location we should be looking at. So now we shift our focus from this wire into this wire because this wire is telling the RAM, okay, where should I be looking at in RAM? So now we track down this wire. And this wire is coming from the output of a multiplexer, which means you have to look at the select of the multiplexer. The selection of the multiplexer is the one wire or multiple wires sometimes that is under the gray dot. Okay? So now the gray dot has a 1, which means input 1 of this multiplexer is connecting to the output. Input 1 of this multiplexer is this wire, and it's coming from the program counter. There's nothing else that can be driving input 1 of that particular multiplexer. So now that we know that the program counter is what is specifying the address port of RAM, and then the content that we are addressing is going into the instruction register. Is that okay? So the way we can code this, okay, now this can be useful. It depends on how you want to represent it. you can always obviously write a sentence about this whole thing, or you can just say that the instruction register is getting whatever the program counter is pointing to. Is that making any sense using C, C++ notation? We are dereferencing using the program counter. The alternative is to say the instruction register is getting RAM location and then the index is the program counter. So either way works, okay? So it all depends on whether you want to consider RAM as the default memory space or whether you want to look at RAM as an array where you can index into. It's your choice, okay? You can use either representation, whichever one makes more sense to you, is more clear, is the one that you can use. And obviously for anyone who only has taken Java, this makes sense because Java has no dereference. If Java is the only programming language you have learned before this class, I'm sorry. I really am, because there's a lot of stuff that you can borrow from C that is really helpful in the explanation of stuff in this processor. Okay, so the rising edge should do this. Okay, so that means when we go back and give it an actual rising edge, we should see the instruction register change from 00, which is the default value after a reset, to 6 F in this case. So I will give it one single clock transition. So it will be a rising edge this time. Control T is the way to do it. And you can see how the instruction register is now changed to 6F. So it is working as predicted. Great. Now we have a falling edge. The only register that is going to do something on the falling edge is the microcode pointer. Okay? So we want to know how are we updating the microcode pointer. So that depends on this multiplexer, because if we choose input 0, then we can have some content that's coming from the register in the instruction register itself. On the other hand, if we choose input 1, then we are just incrementing the microcode pointer. The select point of this multiplexer, or the select input of this multiplexer, is choosing input 1 to be its output. So that means we are following this wire back to the adder. So we are just adding 1 at this point. Yep.
You said that during the falling edge, the only thing that's being changed is microcode pointer.
That is correct.
Is that for this specific
Falling edge.
or is that for all falling edges?
For all falling edge.
Okay.
Yep. So for this particular falling edge, we're definitely incrementing, but in other falling edges, it may get an update from the instruction register instead. But for this falling edge, we know for sure it's just going to increment. So I'm not going to type Control T on the keyboard. And you can see how the microcode pointer is now moving to 001, and location 1 is now addressed. So it changes all of the control signals to the rest of the processor. This is the second beat, so to speak, of the score. So are we still doing okay so far at this point, or are there any questions? Yep.
Wait, how did you know that it was only incrementing?
How do we?
Is it why, like how the box is set right now, or?
It's the only thing that reacts to a falling edge.
Yeah, I know, but the Ucode pointer there can change to something else, like, based off of I think that box there.
Right, because the multiplexer was a 1. The select of the multiplexer was a 1, so that's why we know it is only going to increment.
Okay, so you're just looking at the box for that.
Right. Like right now, we know in the next falling edge, it is going to be taking whatever the instruction tunnel has. Because right now the multiplexer, the select of this multiplexer is a 0, which means it will take input 0 to the output. So the next time for the next falling edge, when the microcode pointer changes, it's not incrementing, it is jumping to some other locations. But I'm not too worried about the falling edge because the next clock edge is a rising edge. So I'm going to look through the rest of the system and say, okay, what has changed? So if you look at the rest of the system, we'll look for enables again. And this time you can see the register bank is still not enabled. The ALU is also not enabled, but the program counter is enabled. In other words, in the next rising edge, the program counter is going to change. When you have a register that is about to change, then the next question is, how is it going to change? Is that okay? So it's a two-stage question. Is it changing? If so, how is it changing? What is supplying the value for this change? So now we want to look at the program counter and say, okay, we know the next rising edge, the next rising edge is going to update the value of the program counter. But how is it going to update? So you look at the D port, it connects to a multiplexer. So whenever you have a multiplexer, you have to look at the selection. And right now the select bit is a 0, which means we are selecting input 0 to become its output. So you track down input 0. It is the output of the adder. The adder is in fact added because it has a 1 as carry in. This is a constant 0, so it is definitely adding 1. So we know the program counter is going to increment by 1 in the next rising edge. Is that okay? But the program counter was used to address the RAM component. So we want to check that too. Is it going to affect the RAM component? So we slide it over, and we can see right now the RAM component is not selected. It's not paying attention. It's not going to do a single thing. So we are not worried about whether RAM is going to do something or not because it's not selected. It's not enabled. Is that okay? Cool. So let's go ahead and do a control T because we do want to visualize and see the program counter incrementing. So control T right there, and the program counter is now incremented to 0, 1. And now we are ready for a falling edge. So every time you have a falling edge, it is the microcode pointer that is going to be affected. So now we have to ask the question, how is the microcode pointer going to be updated? Everything that you need to know to answer that question is already here on the screen. Even though the processor has a lot of gibberish elsewhere, this is all you need. So can someone tell me what is going to be the next value of the microcode pointer after the falling edge?
0.
Sorry?
0.
No, it's not going to be 0. Okay, so we track it down, right? So we know it's going to be updating. So we track down whatever is connecting to the data port. It's coming from a multiplexer. The multiplexer has a selection of 0, which means selection input 0 is what we want. I'm not going to click it because if I click it, you will see the actual value. But I'll just kind of point out that we want to track down this. What is that going to be? There's a splitter, right? But it's a merger in this case because we are supplying information from the split end. The 0 is going into bit 0 to bit 3, okay? Which means the least significant bit of this wire is going to be 0. The least significant hexadecimal digit is going to be 0. Yes?
So we're just going to index off of what's off of the instruction register then? That's 6F?
Yes, absolutely. That's exactly what it's going to do. Because the tunnel instruction is connected to all the other tunnels of the same name. So this is the other end of it. But this end is simple. It just connects to the output of the instruction register. The instruction register has a value of 6F in hexadecimal, which means that tunnel also has a value of 6F. So the 6F is going to go into this particular split end of the splitter. That is specifying bit 4 to bit 11. And then we have bit 0 to 3 being constant 0. So what is the value that is actually going to go in to the microcode pointer? 6F0, very good. Okay, so it's basically the same thing as shifting the value of the microcode pointer by 4 bits. Is that okay? All right, so we should see the ROM module here, or the ROM component, to address location 6F0 after the falling edge. And then we should see the microcode pointer itself to be at exactly 6F0 as well. Is that okay? Are there any questions before I do another control T to single clock to have the next edge? Nope. Okay, so control T, and that's exactly what it does. Okay, so the important part is to understand location 0 of the ROM specifies what we call fetch in the execution cycle of an instruction. So you might want to write it down, either write it down or just have a timestamp and say, okay, tag is talking about the execution cycle of instructions, okay? Location 0 is what we call fetch because that is when we go to RAM, read a byte and opcode, and put it into the instruction register. That's why it's called the fetch cycle. Location 1 of ROM, 001 in ROM, is called the decode cycle because that is when we take the instruction register content, have some zeros to it, and then put it into the microcode pointer. It is called decoding because we are figuring out, okay, where do we go in the ROM as a starting point of that particular instruction. It's called the decode step of the execution of an instruction. Is that okay? Yep.
Is that universal or?
Yeah, it is universal. It's not a tech terminology.
Yeah.
But that's a good question because I do introduce tech terminology in this class. Like the name of this processor is one of those. TTP, text toy processor. Okay, so at this point we are now at the third stage of the execution of an instruction. It's called the execute cycle. In other words, we are at the point that is specific to the instruction itself. Different instructions would do different things at this point. It's the third step of the execution of an instruction. Now, this particular portion of the execution of an instruction can be very short if you don't have a whole lot to do. Or if you have a CISC processor, you can actually have a long step here to perform multiple operations. So this portion depends a lot on what instruction you're executing. It can be short, it can be long, it all depends. Is that okay? All right, but you can also see at location 6F0 in the ROM, the content is quite different from what we have seen before. So now we can go back and say, okay, so what in the processor is going to do something? Because the next clock is going to be a rising edge, so that means we have to take a look at the rest of the processor and not the ROM, the microcode pointer itself. So in this case, the first thing we notice is, oh, okay, the register bank is doing something because input enable is a 1. Okay? Then you go like, okay, but what does that mean? Okay, because we haven't really talked about the register bank as a single component. Well, it is not a single component. It is really just a chip that I made so that I don't have to complicate the circuit of the processor too much. So you right click on this, you go to register bank, view register bank, and this is the inside. So now you can see what en is connected to. It is connected to the enable of the decoder, of this particular decoder. There's only one decoder here. And this particular decoder is using register in select, which is currently 1-1, as the selection of the outputs. So 1-1 is going to select output 3, and that's why output 3 is the only one that has a 1. Everything else has a 0. Is that okay? Do we understand how the decoder works in this case? Okay, so where is that green wire going to, the bright green wire? This bright green wire goes to register D, and it goes into the EN port of register D. So what is that telling you? It's going to be updated, right? Okay. So register D is going to be updated. Every time you answer the question of, oh, this register is going to be updated, the next question is, how is it going to be updated? So now you go back and you track down, okay, where is this wire connected to? Where's the D port of register D connected to? Oh, it's connecting to that pin, register in pin, okay? Which we cannot see why it's getting this particular value. So we have to zoom out again into the main design, and it is this particular pin here. Now, if you have a question of, but I cannot, associate pins of the design to the pins of the packaging itself, the way to find it is to right-click on the chip itself, okay? And, oh, it doesn't show the, interesting. It doesn't show the packaging anymore. It doesn't show the appearance anymore. But anyway, this in is reg in, okay? So reg in, the positions do not change. It's just that the name might have changed. So you track down this particular wire, and you go like, okay, so where is it coming from? It's coming from a mux. So every time you have a mux, you then ask the question of how are we selecting the input for this mux here? Okay? So RI mux is a 0, which means input 0 is connected to the output. So now we track down input 0 of this mux, which is this Y here. You click it and go like, hey, haven't we seen this before? We have seen this before. This is one of those few wires that connects to many, many different components. So we go through the same exercise, okay? Can it be driven by this mux? No, because the input of a mux cannot drive anything. Can it be driven by this demux? Because the output of demux can potentially drive, but this demux is disabled, so it's not going to drive anything. And can it be driven by the D port of the instruction register? Nope, because as an input, we don't drive anything from the input of a register. So then we slide over and we find out that, oh, RAM is selected again, which means it is enabled. And when RAM is enabled, you ask 2 additional questions. The first one is, are we reading or are we writing? Because LD is a high, we are reading. We are reading from RAM, which means D port is driving this wire. So in fact, this is specifying the content. The second question is, who is telling the RAM component to which page we should turn? In other words, we have to track down the address port. So we click on the address port, which we already know is going to go to a multiplexer. Okay, so this is the multiplexer. But this time the multiplexer has a selection of 1, which means input 1 of the multiplexer becomes the output of the multiplexer. So now we track down input 1 of the multiplexer, and it goes to, guess what? The program counter. So this is how the instruction is getting the constant into the register that we want to initialize. Question?
No. I was messing with it last night and I was having problems with the
Okay.
Because the load I stores the constant in the next instruction.
Right. It stores.
2 pointer counterpoints. So.
Yep.
Okay.
And that's why that's why the LDI instruction, even though the opcode is only 1 byte, the instruction itself takes up 2 bytes because you have the other byte to specify the constant that you're actually copying.
Gotcha.
Yep. Cool. Okay, there's one more thing that's enabled. The program counter itself is enabled as well, which means it's going to be updated. So now the question is, whenever a register is going to be updated, you ask how it is going to be updated. So you track down the D port, which is coming from a mux. You look at the selection of the mux. It is now a 0. You track down input 0 of the mux. It comes from the adder. The adder has a carry in of 1, so that means we are in fact adding 1 to the program counter. So this is the part that is kind of iffy, okay? Because on one hand, we're using the program counter to specify which location we should be reading from RAM. And then in the same clock cycle, at the same edge, we are also using whatever is being addressed to update a register in the register bank. Okay? So that can potentially lead to a race condition, because if the program counter is updating way faster compared to how fast your register inside the register bank can update, then you can potentially be updating using the next byte. So this is a potential for a race condition. If you want to avoid the entire actual wait, the entire race condition, then you will have to insert what we call wait states. Now, wait states in a real processor is necessary because RAM takes time. From the moment you change the address and you select and say, okay, RAM, I'm talking to you, it actually takes a little bit of time before RAM says, okay, now the output is reflecting the content of the location that you're addressing. That actually takes a little bit of time, like multiple clocks. So that's why in a real processor design, we have to insert what we call wait states to basically say, okay, program counter, stay where you are. And then we have empty cycles that absolutely do nothing. Okay, it's like clock, clock, clock. Okay, now go ahead and update the register. Okay, but since this is a hypothetical processor, we're not going to build wait states into it. Is that okay? Yep.
How much extra work would that be?
How much extra work you mean to implement wait states?
Yeah.
I would say quite a bit.
Yeah.
The first thing you need to put in is the microcode at location 6F0 now has to include like quote unquote no op cycles, because the microcode pointer will keep incrementing, right? But we don't want it to do anything. So you're basically saying, okay, you have to control all the components. You have to say, okay, program counter stay put. So you have to disable the program counter so it doesn't update. You have to keep enabling RAM so that it has time to decode the address so that it can output the data. And you just keep a few cycles like that until you think there's enough time for RAM to actually output the content of the location. Then you tell the register, now go ahead and update yourself. So it'll be quite a bit of work on the part of the microcode slices, but you can do it. You can definitely artificially insert wait states, but it won't be programmable wait states, which most processors can do. Most processors can program the wait states. So if you're working with fast RAM, you can say, oh, we just need 2 or 3 wait states. If you're working with really slow RAM because you want your product to be inexpensive, you can say, oh, we need 7 or 8 wait states. So the wait state of an actual real processor is quote unquote programmable. In fact, most processors do not even have the main processor directly interacting with memory. It goes through what we call an MMU, or a memory management unit. So the memory management unit has programmable wait state and all kinds of stuff like that. But this is a much simplified processor, and that's why it's not in it. So is that okay? Cool. All right. So this, I just want to identify that this potentially can be a race condition, but it is not in the implementation here. All right. So when we do a control T, what are we expecting to happen? The currently addressed location in RAM should now update register D, and then the program counter should increment by 1. Haven't we seen a description like that earlier today? Let me switch back to the browser, to the instruction opcode table. That's exactly what this is. This is the execute cycle. It is actually doing what the instruction is specifying to do. Okay? All right, switching back to LogicSim, we'll give it a control T. And this time I'm going to go into the register bank, view register bank, and do a control T at this point, because you can see register D actually changing when we have a rising edge. So control T, you can see how it is now A1, which is 161. Okay. Then we zoom back out to main, because the next edge is a falling edge on the clock. So that means the rest of the processor is not going to do a single thing, but the microcode pointer is going to do something. So it's going to increment, right? Because the multiplexer going into the microcode pointer has a 1 as a selection. So that means input 1 is used as the output of the multiplexer, and that's coming from the adder. I'm hoping at this point you're feeling a little bored, even sleepy, because I've been repeating myself quite a few times already. Is that right? If you recognize that I have been repeating myself, congratulations, you have just been paying attention in class. On the other hand, you go like, what? Which counter again? What selection again? What multiplexer? Then I go like, where have you been for the past hour or so? Okay, so you will find that some of my lectures will be like this. I'm repeating the same thing over and over again, but that means you can also have multiple chances to ask questions. If something is bothering you, it's not making sense, there are multiple times you can ask questions. All right, so we'll do another control T, but this time it's special, it is interesting. Because when I do the next control T, you would think that microcode pointer should change to 6F1. 6F1 should be addressed. This should scroll up just by 1. And then we can analyze what's going on when the microcode ROM is at location 6F1. So if I say something like that, it is foreshadowing something, right? What do you think is foreshadowing? Well, it might be happening in the way that you would not expect, okay? So we'll do a falling edge right now, okay? So don't blink. Don't blink. Okay, I know you guys just blinked. That phrase, don't blink, with a lot of intensity, is coming from Doctor Who. There's an episode of the the Weeping Angels. That's it. Weeping Angels. Within that show, they have the aliens where I think they're trying to borrow this from quantum physics, right? So if you're observing something, it cannot do something, but if you're not observing, it would do something. So these aliens, when you look at the alien, they are statues in stone. They don't do a single thing. So you keep staring at it and go like, nothing's happening. You blink, you turn around, you watch, you look at the aliens again, it's closer to you. Yep. So now I have to go to the browser and show you that. Okay, so they're called Weeping angels in Doctor Who. And it is kind of scary to some children. Like this one looks kind of scary. They don't actually hurt people, except for in one episode, when they had to kill people because those people are coming after them. But they normally do not kill people. They basically want to extract energy from people by sending people back in time, like by many centuries. So they don't kill people, but they do erase the presence of that person from the present, and they will throw that person into the past.
Well, how does that harvest energy?
Huh?
Well, how does that harvest energy?
It's just like dropping something, right? High potential going to low potential.
Drop that to the past.
So time has potential apparently?
Time and potential, exactly. So it takes energy to move through time, I suppose.
You're asking why.
And then if you look into weeping angels, there's also meeping angels. It's a Sesame Street Muppet Show thing. So and according to some people, the meeping angel is more scary than the weeping angel. I would agree. Yep. Now you know what I do with my spare time. Okay, so getting back to here. So what just happened? Yep.
So it did go to 6F1.
It did go to 6F1.
Within that instruction, it designate address 0 again.
It did something, correct.
Yeah.
Okay?
And somehow put it back to address 0.
So this is a time when we need to go to the content and actually find out what is at location 6F1 and why is it going back to location 0 in the blink of an eye. Okay, so 6F1. Oh, this is 8. Oh, I can't see. This is what happens when you age. You can't focus close, and because I'm nearsighted, I can't focus far either. So I have a very short range of optimal focus without correction. It's okay. You guys would get there too. So 6F0 is this one. This is 6F1. So 6F1 looks pretty simple. I mean, how can this be doing something so funky? 2 followed by a whole bunch of zeros. Okay, so instead of saying, okay, it's 2 followed by a whole bunch of zeros, let's find out how many zeros. Okay, 1, 2, 3, 4, 5, 6. 6 zeros. Each one is a hexadecimal digit, 4 bits, right? So those zeros are accounting for 24 bits of zeros. The 2 itself is 1 0, so we have 25 zeros altogether, and then the 1 as the most significant bit. Is that okay? So that would make that 1 which bit? Remember we count from bit 0? It would be 25, okay? So bit 25 being a 1 somehow would do something kind of funky. Okay, so why is that? So we have to look at the output of this ROM, and then we ask out of this splitter, where is bit 25 going? Well, here's bit 25. Bit 25 goes to an OR gate first. But this is an OR gate, which means if at least one side is a 1, the output is a 1. Where is that 1 going to? The reset of the microcode pointer. That is why the microcode pointer got back to 0. In the blink of an eye, it doesn't take a clock cycle at all. Is that okay? What is location 0 of the ROM doing again in terms of instruction execution cycles? It's the fetch. What is it fetching? What do you think it's fetching now? The next instruction, which turns out to be 0, 1, or the halt instruction. Okay, very good. Okay, so we're going to do the same thing, but this time I'm going to fast forward a little bit. Okay, so we'll do Control T. So that's fetch. Now we're ready to decode. And now we are ready to execute, right? So you can see at location 0, 1, 0, which is the beginning point of the microcode for the halt instruction, it's just all zeros. So you might think, Tag, did you forget to specify the content at this location? No, I did not. Okay? So now the next question then is, what is that going to do if they're all zeros? Everything is turned off, right? So we know for the rest of this entire processor, everything else is turned off now. RAM is turned off. The program counter is turned off. The instruction register is turned off. Everything in the register bank is turned off. The ALU is turned off. Okay, so for the rest of this processor, it's not going to do a single thing. But then what about the microcode pointer? I mean, for sure it's going to do something, right? Because it's always enabled. The microcode pointer, in fact, is always enabled. But what is it going to do? Let's try to figure out. It's enabled, which means we have to track on the D port to find out how it's going to update itself. Some of you probably can see it right now. It's coming in from the multiplexer. The multiplexer has a selection of 0, which means input 0 of the multiplexer becomes its output. And it is coming in from the instruction register. The instruction register itself is not changing, so we are decoding back to location 010 again. In other words, it is now stuck in the decode/execute cycle because it's kind of the same thing. Which means it's a tight loop. You cannot get out. Yep.
So it's just like checking what the next instruction is, and the next instruction will just always halt?
It's not so much checking, it is decoding whatever opcode is already read into the instruction register. But because we are not changing the instruction register, it keeps decoding it again and again and again, and that's why it's not going to do a single thing. So it's stuck forever. Why are we stuck forever? Why do we have a halt instruction? Where is this idea coming from? It comes all the way from Alan Turing, actually. So we need to go to Alan Turing finite state machine. And I'll just point out a picture of a finite state machine. Not this one. This one is an infinite finite state machine. So I'm going to get one that has a final state. Like, it's not clearly a final state. So I want to find one that has a clear final state that you don't get out of. Oh, this one. This is a good one. Okay, so if you look at S3, which is state number 3, this is the halt instruction. We are at a point where everything is done. There's nothing else to do. Okay, this is a finite state machine. We're not going to talk about finite state machine in this class, but this idea of having a halt or final state, where you can say, okay, I'm done at this point, is coming from Alan Turing, who is the quote-unquote father of computer science. Is that okay? So with a halt instruction, no matter how much we clock, it's going to stay at the same place. So we can go back to the simulator, okay, and we can do Control T over and over again, and you can see how the clock is actually blinking, but we are not moving anywhere. So that means, if your program, when your program has reached the end of what you need to do, if you don't have a halt instruction, it will keep going. Okay? Because just because your RAM location is a 0 doesn't mean it is not an instruction. 0, 0 is in fact an instruction. Which opcode or which mnemonic corresponds to the opcode of 0, 0? No op. No operation. How do you, so what's going to happen? It's going to go to the next location, next location, next location. I mean, surely when it gets to location 255, we're going to stop, right? Nope. When the program counter is incrementing at 255, what happens when you add 1 to 255? When you have an 8-bit register, it goes back to 0. So the whole thing starts over again. So if you don't have a halt instruction and you just let the clock do its thing, unless you put in a tight loop, your program will keep going around and around and around. But if you have instructions that will change RAM locations, somewhere, then they will accidentally try to execute data space as if they are instructions, and that can cause problems. So that's why, at the end of code that you write, you want to insert halt instructions to basically say, yep, this is the end of my code. So do we have any questions at this point about the processor or the LDI instruction or the halt instruction?
Should halt be put for when you're writing assembly code, or is it just?
It is a mnemonic. So if you switch to the browser and you go to the assembler and go to the source tab, you can see the halt is actually a mnemonic. You can just type HALT as an instruction and it recognizes the mnemonic. So that's how I ended this program. Is that okay? Are there any questions about this? Okay, so if there are no questions about this, we'll go ahead and take a look at some of the other opcodes and what they're supposed to do. So here's no op. Okay, so the no op is documented by open and close curly brace, which in C and C++ is a no op, right? Doesn't do a single thing. It's an empty block, doesn't do a single thing. Halt is kind of the same as exit, but it's more like forever a loop. Okay, so in other words, if I want to actually do this more carefully, it is more like this. It's a forever loop that you cannot get out of. Add I is not implemented, so forget about this one. The jump instructions, let's talk about those later. STF is not implemented in the current design. So we'll take a look at some of the other copying type of instructions. You can also read the assembler manual, which has a slightly different presentation, but it does give you the same information, but it does categorize in a slightly more sensible way. So you can read this part here. So we have instructions that can change values by computation. So we have add, subtract, compare, and, or, not, and right shift. So those are the instructions that can do computations, and you can probably expect all of these will exercise the ALU, because the ALU contains all the circuitry for actual computation. We have the other two instructions, increment and decrement. Even though they also make use of the ALU, they do not change the flags, and that is intentional. Okay, you cannot imagine how much trouble I had to go through to say, okay, we want to add one, but we don't want to change the flags. Okay, that turns out to be actually an exercise on its own. And then we have the copying type. LDI is something that we just talked about. We have ST or store, LD is load, and then we have CPR, which is copy register. So copy register is easy. Okay, we are just copying whatever Y is to register X. Remember, Y is one of the 4 registers, and X is one of the 4 registers. Yep.
Are there no loops and like for loops, for instance, in assembly? Is it just done through like jump?
They're all done through jumps. So your so-called structured C program, if you translate it into assembly, it's going to look messy. Yep. Well, there's messy that is organized, and then there's messy that is unorganized. So in the next week or so, we'll start to talk about how to write assembly code in a structured way, so that you don't easily lose track of where you are in your program. Okay. All right. So jump instruction is an interesting one. Jump X is just okay. Remember, X designates a particular register. So jump X is really just saying, oh, we'll change the program counter to whatever that register has. So if this is, okay, let's say we have JMP D, okay? Then whatever register D has is copied to the program counter. So your execution point in the program is now suddenly going to whatever D is pointing to. So that's one way to branch. But this is really cumbersome because before you do a JMP X, you have to load register X with something first. So that's why later on I also implemented JMP II, which is basically saying, okay, it's the same kind of deal like LDI. So you have an immediate constant that is next to the JMPI instruction. Whatever that constant is specifying is what we want to copy to the program counter. So this way we can jump directly to a location without having to put that location into a register first and then do a JMP using that register. So it's a non-risk type of instruction, but it is necessary to make the programs more efficient. Yep.
The eye under the cursor.
Sorry?
Under the cursor, that's an eye, right? Under the cursor.
Under the cursor.
Okay.
Oh, okay, there you go. Okay, gotcha. So the actual thing is program counter. Guess what? Whatever the program counter is pointing to, because the program counter is always pointing to the next available byte that has not been interpreted yet. So that's why the program counter at this point, which is this one, is actually pointing to the constant that you want to put back into the program counter. So that's why this is actually this is the more correct description. This is the more intuitive description of what the instruction does. It's equivalent to a goto in C and C++. You just tell it, okay, go to that continue execution at that label. Or in this case, continue execution at that location. Whatever I is specifies the location where you continue execution. Okay, but that's unconditional. Conditional branches are more interesting. Okay, so let's take a look at JCII, okay, which is conditional branch. But we'll take a look at the intuitive description first, and then we'll take a look at the non-intuitive description. This is the intuitive description. We are potentially changing the program counter. Okay. If the carry flag is a 1, this is a ternary operator, which means if the carry flag is a 1, then we return I as the value of the right-hand side, and then I updates PC, which makes it the same as JMP_II. But if carry is a 0, then program counter is not going to change. We'll just keep the program counter as it is. But that's only the intuitive way to look at it. The actual mechanism is more like this on the right-hand side. So the program counter is going to be updated. One way or another, it's going to be updated. If the carry flag is a 1, then we use whatever the program counter is wanting to at that moment to update the program counter itself. Okay? Which is basically the immediate value that is right next to the opcode of the JCI in this case. If the carry flag is a 0, we just add 1. Because the program counter at this point is pointing to the constant, and we're not using it. So we better skip it, because otherwise, the next fetch cycle will accidentally fetch the constant itself and treating it as an opcode, which is not what we want. So that's why the non-intuitive way is actually a better way to look at it. Is that okay? And I don't think we have enough time to really watch this happen, because it would be great to actually write some code, write one program to intentionally cause the jump to happen, which means we'll end up with a carry, and then write another program to intentionally have the carry flag being cleared so that it continues execution. That can be an exercise for you guys to do. You can experiment. Okay, when you run something in Logisim, okay, 3 things are important. 1, no one's gonna die because you run Logisim. Okay, everyone is gonna die. Okay, but no one's gonna die because you run Logisim. That's the important part. You're not causing. There'll be no property damage. Okay, and as a result, experiment. Okay, that's what I'm trying to promote is. Experiment. You look at these instructions and go like, okay, I wonder how it gets it done. Program it in, clock through the whole thing, watch the whole thing happen. That is how you study at this point of this class. Okay? I don't need to describe things any further because everything is open sourced. You look at this processor, everything is here. You have to follow the line of reasoning to find out how it gets it done. Okay? And the assembler, I don't expect people to really go in and try to understand how the assembler works. That's okay, it's not a big deal. But use it as a tool so that you can easily experiment with those instructions. Okay? So I'll see the late lab people at the lab in a few minutes. And for the rest, I'll see you guys on Thursday.
Okay.